I said in the email and in the post and in the video that you would rewrite this today at lunch. I said yesterday I said tomorrow, but that's today at lunch. But given the road conditions out there, I expected a lot of people to be absent today. Boy, if I had to drive on the highways, I wouldn't have been out there. Well, I guess I would have to be, but I wouldn't have enjoyed it. So I put a post in Google Classroom this morning that if you want to rewrite this quiz tomorrow at lunch instead, that's fine. Whether you're here today or not, I don't care. Okay, so if you were planning on writing it today at lunch, but your day is a little hectic and you don't think you can get ready for it, then tomorrow at lunch. I would just ask everybody, if you're going to rewrite tomorrow at lunch, to plan on rewriting it at the beginning of lunch. Like you have all lunch if you want it, but I have to get you set up right at the beginning of lunch because I have something else going on. Good morning. Good morning. So Andrea and Daniela, I was just making a note that the rewrite for that quiz, if you choose to rewrite it, and I hope you looked at the video and watched all the corrections, I said was today at lunch, but you can write it tomorrow at lunch because there are going to be a lot of people away today. I would ask you to each pick up your quiz here for me, please. And let's do a quick review of the work from yesterday. The work from yesterday deals with sums and differences of functions, and this set of practice problems can be found on page 483. To be honest, I'm really not concerned about number 12 and 13. So if you got to that stage and you were looking at 12 and 13, I mean, I can go over them if you like, but it's not a big deal. With function operations, when we're talking about sums and differences, when we have f plus g, quantity of x, it means f of x plus g of x. And it means that the new function is simply found by adding f of x and g of x. That's all. You're just adding the two functions together. And the order of addition doesn't matter. If you see something like f minus g, quantity of x, that means you're going to take the function f of x and subtract the function g of x to get the new function, but order matters. Is it clear that when you add things together, it doesn't matter the order in which you add them, but when you subtract, it makes a difference? No pun intended. When you subtract, it matters? Okay. Now, this is something that I don't want to overload you with in the first lesson of this chapter, which was yesterday's lesson, but the domain of the resulting function is the domain that is common to both functions being added or subtracted. And the reason is, we saw graphically yesterday that what you're doing when you find f plus g of x is you're going to a particular value of x and you're adding the y coordinates. So in order for you to be able to add the y coordinates, both functions have to exist in that location. If they don't exist, if one of them doesn't exist, then there's no way you can add the y coordinates. I'm going to talk more about that later today. That's called the domain rule. And this is an important thing. I would say pretty much throughout this whole chapter, there's no nice, tidy way for you to find the range of the result of operations on functions, or what we will learn about later in the week, which is called compositions of functions. You just can't do it. I think we're going to be starting compositions tomorrow. Now I have this, and you don't need to furiously write this down. I can print these out if you like. This looks exactly the same as what I just said, but now I'm saying f plus g of a is equal to f of a plus g of a. I'm being more specific. I'm saying, for example, that if you were ever asked to determine f plus g of 4, what that means is you're going to find f of 4, and you're going to add g of 4, which we're going to go around in circles on this. You should recognize f of 4 is the y coordinate on f when x is 4. And you should recognize that g of 4 is the y coordinate on g when x is 4. So we're back to that idea of adding y coordinates. And the order doesn't matter. We can say the same thing for subtracting. Right? If I said, what is g, I guess I'll go in the order we have here. What is f minus g of 1? Then you would find f of 1 and subtract g of 1. Go ahead.
Let's say the question was f subtract g of a, and then you accidentally did g subtract f of a. Would you be able to just take the answer and switch the signs?
Yes. One of the things I mentioned yesterday in the video was I made a big deal of saying that I think I wrote it as f of x minus g of x is not equal to g of x minus f of x. It's not a stupid question. It's a great question. I'm pretty sure what I wrote. But I could have written f minus g of x is not equal to g minus f of x. They're not the same, right? And what Farhan is saying is, could I find the one that's not correct and multiply by -1? And the actual answer is yes, because if you think about this, and this requires a little bit of thought, if you take f of x, whatever the graph looks like, and subtract g of x, you're going to get a series of y coordinates that trace out a new function, right? But if you were to take those same functions and you were to take g of x and subtract f of x, you'd be subtracting the y coordinates of g minus the y coordinates of f, and all the numbers would be negative. What that means is the graph of f minus g of x will be a vertical reflection of the graph of g minus f of x, because all the y coordinates will have been flipped. So in fact, I could say this, and this gets to the heart of your question and I hope answers it. This would be a true statement. And this is actually a good diploma exam question. I mean, I don't know exactly how I would structure it, but you should understand that this is not necessarily true. I guess you could probably come up with some weird functions where it wouldn't matter if you subtracted them one way or the other. I guess it wouldn't be weird functions. You would just have to have two functions that were the same. You know, and in which case when you subtracted it, you get y equals 0 all down the line. But you should know that's true. Again, the domain is the common domain, and the range can only be found by looking at the resulting graph. So if I were to take a look at this particular graph, and I said, what is the domain of f plus g of x? When we take a look at g of x has a domain that can be described on a number line or can be described with a one-dimensional graph by saying x is any value of -6 or greater. You can see that on the graph, right? And when I start taking a look, so these are domains, when I start taking a look at, the colors aren't going to match here. I'll just use black for f of x. If I look at the domain of f of x, the domain of f of x is any real number, right? That absolute value function, which is what it is, goes on forever to the left and the right. So where do these domains overlap? They overlap starting at -6 and going to the right. Because if I said to you, go ahead and find the new y coordinate when x is -8, you can't do it, can you? Because you're supposed to, if we stick with h of x, add the y coordinates, but g of x doesn't exist there, so you can't have a y coordinate to add. It's not defined there. So h of x is not defined there. Getting now to my error in the video. This is a page. I got something that moved there. I don't know why. This is the page that you would have been seen in the video, and this point was not a point that I originally plotted. It was just I put it in there later. But I made a big deal about y equals root of x minus 1 being root of x shifted 1 to the right. So the vertex, I'll use black here to indicate it, was here. You go up 1 and over 1, and then you go up 4 or up 2 and over 4 and up 3 and over 9. But unfortunately, I had the ordered pairs in my head that if you go up 2 and over 4, it's at 2 comma 4. And it's not at 2 comma 4 because it's shifted 1 to the right. This point, this green, I'll get rid of this. This green point, if I can get it, this green point should be here. So this curve is going to be off a bit. And similarly, this green point, which I put at 9, should have been at 10. So the curve of the function actually is a little more severe. And I believe, and I posted this in the edited description of the video on my YouTube channel, I believe that if you then this part of the graph here, the red graph is good. But I believe if you would have done y minus y for the curve minus the straight line, this would have been more severe. Okay, but it doesn't affect the overall result. Well, it affects the overall result. I'm not going to kid myself. It doesn't affect the content of the lesson. So, with that being said, does anybody have any questions you would like me to explain or go over or help you with on page 483? Go ahead.
Can you go over how to determine the equations from that graph with the one that you had up?
Okay. So if you wanted, let's just say the equation of f minus g. Like, so we're talking about this, which is not necessarily an assigned question. It might be, actually. It is? Okay. So, but we won't worry about trying to hunt it down. Let's just worry about what the equation of, say, f minus g is. So k of x, let me ask you a question, Sienna. If this was in the assigned problems, were you given the equation of both of those functions? Okay, so that's something we have to do, and that's really not the point of this lesson. However, these are previous skills you've learned. When you take a look at the square root function, you should recognize that curve as a square root function. You will notice it has that square root pattern to it, that you go up 1 and over 1, you go up 2 and over 4, you go up 3, and it will be over 9. Okay? And that means that it is merely going to be for g of x a transformation of the square root of x of 5 units to the left, which means this is the equation of the function g of x. Now, when you look at f of x is going to require a little more work. F of x is an absolute value function. And the absolute value of x, I better move this over. I'm not going to worry about the fancy colors. The absolute value of x is a graph that goes through the origin, and it has a slope of 1 in quadrant 1 and a slope of negative 1 in quadrant 2. We can see that this absolute value function has been stretched in some way. And what I could say is that normally you would go from the vertex 1, 2, 3 over, and you would go 3 up. But this is going 6 up to get to that slope, which means that we have an a value of 2. Things have been vertically stretched by a factor of 2. Then what we can see is that afterwards that vertex ends down at negative 3, which means the thing has been shifted down 3 units. I'll be honest with you, in this unit, you do need to know how to find those equations. But in this unit, it's more likely that you're just given the graphs. And I don't want you to think you have to find the equations, because I could give you the following graphs. And I'm not going to take time to make a grid, but I could give you the following graphs. No, let's do this. And say to you, sketch f of x minus g of x. And the point I want to make here is you can't find the equations of those functions because they're piecewise functions. I don't want to get into piecewise functions, but each little segment of that f of x is defined by a different equation. So there's no simple equation to write out what f of x is. Anyway, getting back to this, now that you know f of x and g of x, for k of x, we take f of x minus g of x. And, you know, typically what will happen is you end up with something that there's nothing you can do to this to simplify this. This isn't even apples and oranges. It's dollars and kittens and clouds. They're three different things. They're absolute values of x. They're numbers, like -3 integers, and they're radical functions, and that would be it. Okay. Other questions? Go ahead, Farhan. Yep. So what's happening here? In every example I gave you yesterday, I gave you two functions and asked you to find the sum, right? But I think what's happening here, or difference, what's happening here is you're told the sum. Did you say D? B. So you're told h of x in B is equal to the square root of x plus 7 and then plus 5x plus 2. And f of x in B, well, f of x in the question is 5x plus 2. So how many of you see that g of x is root x plus 7? So to some people, it's just, I mean, it's there, right? If h of x, you're told in the question, is f of x plus g of x, and you've established that f of x is the square root, nope, and you've established that g of x, because it says in the question, oh no, I got these backwards, don't I? I should switch them this way. Because f of x is... So, I mean, there is a little bit of processing that has to go on here. You have to understand that you can add these in any order. There we go. But now we've established that one of these two functions that's being added is f of x. So the other function must be g of x. G of x must be root x plus 7. If you're looking for an algebraic way to do this, I would say we can do an algebraic solution, but I think it's making it more involved than it needs to be. Yep.
We have to use the algebraic solution for D and C.
This would not be a written response question. There's nothing to it.
First, how would you do D? I guess that one's...
How would you do D? Without an algebraic solution, just looking at it? Okay. What you would be doing, I'll kind of set this up as an algebraic approach. What you would be doing is you would be saying, I need to get this function by taking f of x and adding g of x. And f of x is 5x plus 2. So, I mean, we're almost there with an algebraic solution, but just by inspection, what would we have to add to 5x plus 2 to turn it into this expression on the right? And we would have to add a 3x squared, wouldn't we? There's no 3x squared over there. We would have to add negative x because we want 4x and there's 5x there. What would we have to add to 2 to make it into negative 2? negative 4. So, I admit that in this particular question, I think algebraic is better. I think it's better to just rearrange this for g of x. Just subtract 5x from both sides and subtract 2 from both sides. Are you okay with that? Okay. Any other questions before we go on today? So is it safe to say that this was fairly straightforward? Okay, that's good. All right, we're going to be looking now at products and quotients of functions, and this is on page 13 of your unit handout. Products and quotients of functions get a little bit more involved, but I will tell you right out of the gate that the whole concept of working with y coordinates when you're adding or subtracting functions is what we're going to be doing when we're multiplying or dividing functions. It's going to be all about y coordinates. So we're looking today at basically the product or quotient of two functions and your ability to sketch the graphs, determine domain and range, domain and range, and also write the equation. Listen very carefully, write the equation if I give you the equations. We're not concerned with coming up with the equations. So I want to review something here about the 4 basic operations in math. When you have the word sum, we know that that means you're adding things. When we have the word difference, we're subtracting things. There's a word for what we get when we multiply things together, and that word is product. And there's a word for what we get when we divide, and that word is quotient. When you add or multiply, the order is unimportant. As I said yesterday in the video, there's a word for that in mathematics. It's a commutative property. It means that the order is unimportant. It's not going to change the outcome. But we know that when we subtract, order matters, and you should know that when you divide, order matters. If I say what is 10 divided by 5, the answer is 2. However, if I say what is 5 divided by 10, the answer is not 2. It's 1/2 or 0.5. I'm going to add something else to this. As long as you have 2 things to add, I want to make that clear. As long as you have 2 things to add, there are no numbers that we deal with that you're not allowed to add. Positive numbers, negative numbers, square roots of numbers, as long as the square roots are defined, you can add them. When you subtract things, if the 2 things are defined, you can always subtract them. I'm qualifying that with if the 2 things are defined, because when we talk about graphs, if there's a region where one function doesn't exist, you can't subtract the functions. And when we multiply functions or multiply things, we're always allowed to multiply them. We're always allowed to get a product as long as we have 2 things that exist that are being multiplied. But there's an exception for a quotient. You're not always allowed to divide any 2 things that are defined. And you already know when you can't define a quotient, and it's when you're dividing by 0. So we're going to have to remember that when the denominator of a function is 0, we have a non-permissible value of x producing that, and that means the function is not defined there. So the definitions are the product of 2 functions is written as, now that dot is just pronounced times. It's just a different way to put a multiplication symbol, but we usually put a dot. It's a solid dot, that's important. So f times g, quantity of x, means f of x times g of x. And I'm not going to write this out, but I think it's pretty obvious that I could write this as g of x times f of x, because you're multiplying. Who cares the order that you write them in? Oh, I've got that right there. I mean, you can make a mental note that f times g, quantity of x, and g times f, quantity of x, have to be the same. I want to make a really strenuous point here that that dot is a solid dot. You cannot be lazy about drawing this or writing this on a paper. Because later on, we have a symbol that's an open dot, and it means something totally different. It's outside of the realm of adding, subtracting, multiplying, or dividing functions. So these 2 things are not the same. So when you use the function notation for the product, make sure that dot is very clearly filled in. The quotient of 2 functions can be written as f over g, quantity of x, and that means h of x would be f of x over g of x, and you should make a note that these two things are not equal. I think I know what you're going to ask, but go ahead.
Just like subtraction, if you reverse it, the absolute value would be equal to the absolute value. For that, would f over g of x be equal to 1 over g over f of x?
Yes.
All the time, though?
All the time. Well, no, because they may have different non-permissible values. So first of all, the answer to your question in general is yes, and you learn about that. What you're talking about is a reciprocal function. Is that coming from in here or out there? It's out there, eh? That's loud. You learn about reciprocal functions in grade 11. So yes, it is true that if this is, say, h of x, and this is, say, k of x, that h of x is the reciprocal of k of x in general. But we don't want to say they are always equal because of the following. Non-permissible values of h of x will be found by looking at g of x and where it's 0. Because if g of x is 0, h of x is not defined. But when I flip the thing over, at that point that was not defined, maybe now it is defined because g of x is now in the numerator. So when I go over to k of x, I'm going to be looking at the denominator for non-permissible values. So the graphs might be different depending on the non-permissible values and the zeros of the two functions. But we're going to get to that a little bit later. Okay. Are you satisfied with that though for now? Okay. And I'm just making a note here that f over g quantity of x is f of x over g of x, and g over f quantity of x is g of x over f of x. So now we have this thing called the domain rule. And we could have used the domain rule, and I want everybody to focus up here. Don't worry about getting ahead in the lesson, please. The domain rule is something that I've already explained to you at the beginning of the class. I told you that the domain of the sum of two functions is the domain that's common to both, the overlap of the domains. Because you can't add things that don't exist. And what I'm going to tell you is that this rule, this thing that I'm saying, which is the domain of a product or quotient of two functions is the domain common to both, is the same as what we were doing yesterday. Okay? Except, this is not a complete domain rule. Because if both of the functions are defined for a quotient everywhere, there could still be a point where the quotient is not defined. Let me give you an example. This is going to start to get a little bit tricky. But if I looked over here, and you know, I can print out this page once I've filled it in. You don't need to copy it. I'd rather you just think and listen. This was the same one we were looking at earlier, wasn't it? Pretty sure. So one of these functions, I'll use the color that matches this time. G of x is defined everywhere. So this is g of x from and including -6 up to and including, well, infinity. Whereas, I don't know if that color is going to be perfect. Whereas f of x, which is the bluish graph, extends from -infinity to infinity. So what is the domain of f plus g of x? Well, it's x is greater than or equal to -6 because that's the common domain. Just give me a... Is it -5? Oh, thank you. It's -5. Was it -6 on the other one? Oh, it was -5 there too. Okay. Just can't read the graph. So it's x is greater than or equal to -5. So the question I have for you is, do you see what I mean by the common domain? It's where the two domains overlap. And that would be the domain here, and that would be the domain here. But it would not be the domain in any of these other two. See, we could say for y equals f of x over g of x that x definitely has to be greater than or equal to negative 6. You cannot, in this region over here, start dividing the y coordinates because one of the y coordinates doesn't exist there. But for f of x over g of x, we cannot use negative 6. And I want everybody to think about why we cannot use negative 6. Negative 5. Once you get a number in your head, it's in there. We cannot use negative 5 in f of x over g of x. Why is that? Sienna, nice and loud, please. Right, at g of x, right? The one we're dividing by. So if I said we're going to take the y coordinate of f at negative 5, it's 7, and the y coordinate on g at negative 5 is 0, and you take 7 over 0, we can't do it. So I'm going to go back now to my domain rule and add, and this is in your notes, the domain of a quotient is further restricted by excluding any values where the denominator is equal to 0. By the way, you can make a mental note or a physical note that the places where the denominator is 0 are the x-intercepts, right? So any place there's an x-intercept for the denominator, that cannot be part of the domain. So going back to this is the domain of f of x over g of x on a number line. You know, it could be indicated that way. Now, what about g of x over f of x? So let me get rid of some stuff here. What about f of x? No, what about g of x over f of x? The last one. Well, I can divide these y coordinates. I can divide these y coordinates. I can divide these. I can divide these. I can divide these. But I cannot divide the y coordinates here at what I'm going to say is negative 1.5. Because I would be taking the y coordinate of g of x, which is about 1.9, dividing by 0, and that's not defined. And again, we're back to the idea that the denominator function, wherever it has an x-intercept, the y coordinate there is 0, so you can't divide by 0. And that would mean we could write here for the domain, we could say x is greater than or equal to 5. It can be equal to negative 5. It would have a value of 0 because you'd be taking 0 over some other number. But then you would have to say that x cannot equal. I'm just going to read those 2 points as negative 1.5 and positive 1.5 for my explanation, plus or minus 1.5. And putting that on a number line would be a little bit more work. At negative 5, the function exists. At negative 1.5, I'm not going to worry about drawing this to scale. And at positive 1.5, the function does not exist, so you would probably draw something like that. So does everybody understand the domain rule? You have to add that extra part for whenever you're dividing. Any questions with that before we get started with the examples? All right. So example 1, consider the functions root x minus 1 and x minus 2. What's the domain of each function? So the domain of f of x, I will explain how I'm getting this, but this is something you should definitely know how to do, will be x is greater than or equal to 1. And I'm doing that by taking my knowledge of what the graph of y equals root x looks like, and taking my knowledge that root x minus 1 is shifted 1 to the right, to figure out that f of x which is root of x minus 1, will look like that. You could use your graphing calculator, I suppose, but I don't think you need to. With g of x, the domain is x is any real number. If you want to put negative infinity to infinity, you certainly can, as long as you use round brackets. And if you write that on its own, it's always a good idea to throw an x in there so people know you're talking about domain. So now, what is the domain of the product? Or what is the, we're not there yet. That's the domain of each function. Are we okay with that? All right. Write the equation of f times g of x. Well, that just means f of x times g of x. This is h of x. It's equal to f of x times g of x. You don't need to put a multiplication sign between them when you separate out the two functions. So h of x is f of x multiplied by g of x, and there's not a whole heck of a lot you can do with that. I mean, could you FOIL it out? Yes. It just occurred to me, I didn't really explain why the domain of g of x is any real number. You should know that x minus 2 is a linear function, so its domain is any real number. What's the domain of both multiplied together? Well, if f of x is only defined from 1 to infinity, and g of x is defined from negative infinity to infinity, and by the way, you don't need to draw this, but it's a nice way to look at things, I think. Then what is the overlap of the two domains? Well, it would be from negative 1 to positive infinity. So the domain is going to be x is greater than or equal to 1. I might have said negative 1 a second ago. I meant 1. I'm not going to use class time right now to confirm it on your graphing calculator. If you did, you'd get a really weird looking function, but it would only exist from 1 to infinity. Question? No? What's the equation of f over g? Well, that's easy. K of x is f of x over g of x. That's it. But we should probably put here, just like we would with a rational function, and this isn't a rational function in the strictest sense because it's not a polynomial on the top. It's a radical on the top. We could call it a rational function if you like. As with any function that has a variable denominator, we should, when we write the equation of the function, state the non-permissible value. What's the domain rule have to say about this? So let's talk here about, again, f of x being defined everywhere from 1 to infinity, and g of x being defined from negative infinity to infinity. So the common domain would be x is greater than or equal to 1. But we have to exclude any values of x where g of x, the thing we're dividing by, is equal to 0. And you can see that when you take a look at the denominator, that means we have to add the statement that x is not equal to 2. We wouldn't put up here at 2 some kind of open dot on g of x because g of x is defined at 2. But g of x at 2 has a value of 0, which means the denominator will be 0, so k of x is not defined. Any questions with the domain of k? All right, example number 2, we're given two functions. We're asked to determine f times g of x. So we have to take f of x, which is x plus 2 quantity squared minus 5, and multiply by g of x, which is 3x minus 4. I'm using the large set of brackets because f of x has got multiple terms. And now, unlike the previous couple of quotients or products, where you can't really simplify them, this we can. You can simplify what's in brackets here for f of x by foiling out x plus 2 squared and taking away 5, and then multiplying that by 3x minus 4. When I take x plus 2 quantity squared, don't forget it's x plus 2 times x plus 2, which is going to give us x squared plus 2x plus 2x, which is 4x, plus 2 squared is 4. And then we have to subtract the 5 and multiply by 3x minus 4. So what we're really doing here is kind of maybe grade 9, 10 algebra. Probably grade 10 because it's going to be cubic. We can simplify this a little bit into x squared plus 4x minus 1 by 3x minus 4. And then we're going to have to multiply this out. And that means you have to use the distributive property and multiply everything in the first set of brackets by everything in the second set of brackets. So it's time to be slow, methodical, careful, deliberate. It's time to really be thoughtful about what we're doing here. I just start with the x squared and I go x squared times 3x, which would be 3x cubed. I take x squared times negative 4. And then I say to myself, I'm done with the x squared. And we'll double check 3x cubed, negative 4x squared. Now I move on to the 4x. 4x times 3x is 12x. And I might as well stack that with the other 12x squared. Stack that with the other 12x squareds, or the other x squareds. 4x times negative 4 is negative 16x. And that tells me that I'm done now with the 4x. So now I move on to the negative 1. Negative 1 times 3x is negative 3x. Negative 1 times negative 4 is 4. And basically, when you add all this together, you've got the answer to the question. It's going to be 3x cubed plus 8x squared minus 18x plus 4. Does that look okay to you? No? Yes, it should be 19. Thank you, Mackay. Definitely. We take a look now at the next part of this question. Whoops. It also said, what's the domain and range? And remember, we don't have a range rule. There's no range rule, okay? But I'm including range here because we can determine it. First of all, both of these functions, f of x and g of x, have a domain of any real number. The first function is quadratic, so it's a parabola that moves to the left and the right forever. The second function is linear, so it is a straight line with a domain of any real number as well. So the overlap of those two domains would be x is any real number. They're defined everywhere, so the product will be defined everywhere. So we can put down here x is any real number. Now I happen to know that y is any real number as well, and it has nothing whatsoever to do with anything we've been talking about in this unit. It's that this is a cubic polynomial function. It's odd. Yeah, it does that. Exactly. The two arms go in opposite directions. The right arm is going up because it's positive 3x cubed, and because it's an odd degree, x cubed, then the left arm goes in the opposite direction. So we can still expect you to find the range here. Let's take a look at example 3. F of x is x squared. G of x is root 4x minus 5. What is the product? I mean, this is... When I asked you earlier, was the stuff you did yesterday pretty straightforward? I hope this is pretty straightforward as well. You're just deciphering... Well, you don't even have to decipher here. I didn't even put this. I could have put that. The fact of the matter is you could probably have answered the first part of this question without knowing anything about operations on functions. So we're going to take x squared, which is g of x, and multiply by root 4x minus 5. I'm sorry, my mind's all over the place this morning. X squared is f of x, and we're multiplying by g of x. That's it. There's nothing you can do with that. Well, there's something you could do. You could take that x squared and write it as x to the 4 and put it inside the radical. But I'm not sure what your motivation for doing that would be. That's it. What's the domain and range? Well, we're not going to look at graphs to find the domain for each of these. You should know that f of x has a domain of any real number. And you should know how to find the domain of g of x. Because a radical is only defined if the radicand is greater than or equal to 0. Right? You cannot take the square root of a negative, not in high school. So I solve this little inequality and I get 4x is greater than or equal to 5, which means x is greater than or equal to 5/4. So that's the domain of g of x. I think at some point, just when we're doing a multiple choice or a numerical response question, or we're working on our own, you should not need to draw a number line showing both of these domains to know that the domain of the product will be x is greater than or equal to 5/4. Because that's going to be the overlap. I think on a written response, that number line will really help communicate. That number line eliminates the need for you to start writing a whole bunch of words about the overlap of the domain. You might want to still put something, but you don't need as much. Any questions with example 3? Go ahead, Jason. Oh, we never did the range. Okay, so thank you, Jason. I'm debating whether the range here is important in terms of what we're learning, but I will discuss it. The range is going to be y is greater than or equal to 0. And let me explain why that is. This function here, this piece will always either be 0 or a bigger number than 0. X squared will always be 0 or a bigger number than 0 because it's being squared. And the square root can never be negative because it doesn't say plus or minus. So algebraically, range is a really complex beast in mathematics to look at an equation and determine the range, because everything is there's a different rule for every type of function. So what we could do is reason that out, that since these two things, these two quantities are both going to always be, they'll never be negative, the product of them can never be negative. Okay. I would say to you, though, that the best bet here for range is to look at the graph. And that's what I would always say to you. In fact, I think I said earlier, we don't have a domain, we have a domain rule, but we don't have a range rule. You need to pretty much look at the graph to determine the range. But thank you for reminding me that we didn't do the range there. Any other questions with example 3? Okay. One more example. We have two functions. One is quadratic, one is linear, and we're asked in A to determine the equation of h of x where it's g of x. I'm just going to write this here. H of x equals g of x over f of x. Well, g of x is 2x plus 6. F of x is x squared plus x minus 6. Make sure I transposed that or transcribed it correctly. G of x over f of x. Yeah, it looks okay. We're okay with that? Can we simplify this? Definitely. And we're back to Math 20-1. We're back to the stuff we reviewed in Chapter 9. A rational expression can be simplified by factoring everything completely. In fact, yesterday when we were in Math 20 learning about rational expressions for the first time, I had one screen that just said factor. And anytime someone would say, I don't know what to do, I'd go to that screen. You have to factor before you can do anything with rational expressions. I can factor a 2 out of the numerator and be left with x plus 3. The denominator factors, it's a what I call a simple or basic quadratic trinomial, where you would be looking in this case for two numbers that multiply to give -6 and add to give 1. I believe those are the numbers. So we can cancel a factor that appears in the numerator and denominator. We okay on the factoring and canceling? Good. So are we okay with me saying that h of x is equal to 2 over x minus 2? You okay with that? Because you shouldn't be. Because that's not h of x. If I were to graph this, I would get a graph that passes through -3 for x. But x cannot equal -3. Remember your non-permissible values, which is going to be related in some way to domain here in a second. Your non-permissible values are always found pre-canceling. And we should maybe also write +2. You might look at that and go, well, do I really need to write +2? I can see there's an x minus 2. The answer is yeah, you should. So this is h of x. Any questions with A? Go ahead, JV.
Yeah, so like when you canceled like the x plus 3, would that result in a whole?
It is. And that's going to be what we're going to talk about in C. And what this question is doing is connecting what we're learning about quotients of functions with what you learned about non-permissible values in rational functions. Have I answered your question? Okay. Any other questions with A? All right, B, determine the function of k of x. So now we want f of x over g of x. So f of x, I'm going to ask you for your help here because my memory is not what it used to be. I'm pretty sure that f of x was x squared plus x minus 6. And g of x is 2x plus 6. I hope you understand we're going to get the same result, but it'll be upside down. Okay. So we will have k of x is equal to x plus 3 times x minus 2 over 2 times x plus 3. Same dealie as before. We end up with k of x is going to be a linear function. One half x minus 1, but written as a rational function. However, we should say x cannot equal to -3 because we had -3 as a 0 in the denominator of the factored form of the function. So, any questions with B? C, this is a very open-ended question, and this is just my opportunity to make that connection between this stuff and what we learned about in the last chapter. We had, on the one hand, h of x simplifying, well, I'll write it out. We had 2 times x plus 3 over x plus 3 x minus 2. How's my memory on that for h of x? Good. And we had for k of x, obviously, the reciprocal, which is what Farhan had pointed out at the beginning of this. These are just reciprocals of each other. We end up with x plus 3 over, whoops. We end up with x plus 3 multiplied by x minus 2 over 2 times x plus 3. So when we are asked to analyze these two, what we would do is start talking about the important features of the graph. And h of x has a hole at -3. and a vertical asymptote at x equals 2. This was quiz material from yesterday, right? Factors that cancel lead you to a hole, and the hole will have an x-coordinate that's the 0 of the factor that canceled. Factors in the denominator that do not cancel lead you to a vertical asymptote, and factors in the numerator that don't cancel lead you to an x-intercept. So over here, you have a hole at -3 again, and you have an x-intercept at 2. That's basically the analysis. We could go further and determine the equation of the horizontal asymptotes, but I'm not interested in that. I want to point one last thing out to you. That this function has x-intercepts of -3 and 2, and this function has an x-intercept of -3. Anytime you divide two functions that have the same x-intercept, you're going to get a hole where that is. Anytime you divide two functions that have the same x-intercept, you're going to get a hole. Because if function 1 has an x-intercept at, I'll say 5, that means there's an x minus 5 in the numerator of that function. The value of 5 makes that function 0. If the second function also passes through 5 on the x-axis, then that means that 5 is a number that makes that function 0. Which means there has to be a factor of x minus 5 in that function. So when you divide the two functions, if each one has an x minus 5, each one will cancel, and that's the definition algebraically of a hole. I'm going to come back to that. I'm going to stop there. I'm going to come back to that and talk about that at some other time, because it's going to come up where you do not have the equations of the functions, but you have graphs. I wonder if I can do it right now. Absolutely. If you take a look at this function, will this function have a hole? It will. It'll have a hole at -1. Because think about this. If g of x passes through -1, g of x must have a factor of x plus 1. It has to. Now, it's probably going to have some other number to give it the right slope. No, the slope is 1. That would be the equation. If f of x has an x-intercept of -1, then it has to have a factor of x plus 1. It also happens to have a factor of x minus 1. There could be some other parameter out in front, but it's unimportant. If you divide those two, they each have x plus 1. So you're going to get a hole, and they both have the same x-intercept. Anyway, you've got about 15 to 20 minutes here to work on these problems. I don't think you need to do any sketches of graphs. Certainly, if you see a graph, you have to interpret it. Any questions?